So in this video, we're going to talk about what if your time series data has seasonal variations in that. So there's lots and lots of examples of historical data would have seasonal variations. You can think about, extreme versions like, selling snowmobiles would have a higher season in the winter than in the summer and so forth. And so we'll use a method called Winter's method that is able to adjust our estimate to accommodate these seasonalities in our data. And so my first question to you is, why can't we use, our previously studied models? Why can't we use exponential smoothing with a trend, for example, if you had, seasonality in your data set? Hopefully, if you think about this, and let's think about maybe sales data, and let's say you had a really high peak in November and then December, and then in January you have a low time. If you use the previous models, it would interpret the seasonal rises, what happened in November and December, as permanent. And so it would then overshoot our demand estimate in January when January is maybe our slowest month. And so we need to fundamentally capture the fact that there is the seasonality. November and December are high, January is low. And so we need to adjust what we predict in the future to accommodate that so that we don't over or undershoot things thinking they're permanent when they're just a seasonal impact. And so what we're going to do that is what's called Winter's method, which captures trend and seasonality corrected exponential smoothing. And so, here's an example of some data that has both a trend and seasonality. And this is actually US retail sales in millions of dollars. And you can see over time, we buy more stuff, we sell more things in the US. So there's an upward trend. But if you look at this, there's this repeatable pattern. And if you look inside, you could see the peaks are that holiday I'm talking about, November, December, and then January is a slow month, December, and so forth. And so if you think about that, if you only incorporated there was a trend, you would miss, you'd be off on those months that go down. And we'll talk more about how to capture this. But if you have data that has these three systematic components, a level, which remember all time series data have a level. You can think about, I can take the average, that's the level. If you have a trend, either an upward or a downward trend or seasonality, then Winters is an appropriate forecasting method. In this class, we're going to study this type of Winters method, which we are going to mathematically talk about, but kind of generally, we're going to combine these three systematic components in this way. We're going to add level and trend, but then we're going to multiply the seasonal factors. And so, mathematically, you can see there's these seasonal factors S, and we're going to multiply that. And so this is sometimes called a multiplicative model. And so one thing to note when we do study this in R is we need to make sure you set seasonal equals multiplicative. So that's one thing. Another thing to note is there are other forms, functional forms of Winter's method. And so keep that in mind. And so if you think about these seasonal things by multiplying, what are they doing? You can think about in our data, if this peak is December, you would amplify what I expected. And then you would think, okay, on the lower one, you would de-emphasize it. So you could think about these as kind of weights. Should I multiply something more because it's a high demanded season period? Or multiply it by something less than one, and that would make it less than what I was expecting if there wasn't a season. And we'll see that mathematically. All right, so just as an example, so thinking about a hospital, they also have a season, and it repeats every 12 months. So it has a yearly season. And so this is some data that is inpatient days. And so January, February, etc. And so this is the actual inpatient days for different months. And you can think about, okay, how are we actually going to forecast this? So let's say this is for, this year, what are we going to do next year? How would we do this? So again, there are three systematic components. We have a level, a trend, and a seasonal factor. And so what we're going to do is we're going to break this data into those three components. And so let's first just break up the trend. So if I got rid of the seasonality, and so I de-seasonalized it, sometimes what it's called, this is what it would look like. So there is an upward trend in my data set. And then if I just look at the seasonal aspects, you can see these are what's called seasonal indexes. And so what you can see here is if the value is greater than 1, that means that month is on average bigger than we would expect. If it's less than 1, it's less than we could expect. And so if your data did not have any seasonal, what you would have for seasonal indexes is they'd all be 1. I don't want to adjust them. There's no seasonality in my data. I don't want to adjust them. When you have seasonality in your data, what we're doing is we're basically saying, okay, this month is a higher than usual. This one's a lower than usual. And so if I sum up all of these seasonal indexes, what do I get? I should get 12, okay? And so you think about, I'm basically normalizing how much weight should I have for each of these different periods. And so then you could combine them together, and this is just the original data that combines both of those things together. Okay, so how does that work? One thing that's new in this method that we haven't talked about in previous methods is we have these seasonal factors. So let's spend a little bit of time talking about them. So seasonality corresponds to a pattern in the data that repeats at regular intervals every P period. So if you have a yearly seasonality, then P would be 12. Every 12 months, I get this component. If you have, a day and you work 8 hours, maybe the morning shift, morning 8 a.m. is different than the 3 p.m. P can be different values, but it has to be repeating and it needs to be in regular intervals. This is what in Holtz-Winters function is known as a frequency, and that is something you have to set. So you have to look at the data and you have to set my frequency is equal to whatever. And so I will say this is the kind of little bit of extra challenge you have with Winters method. And then we're going to again use the multiplicative seasonal factors. And so for each period, so we'd have P of them, 1 through P, we need some sort of factor, right? And so we have the first period of the season, second period of the season, all the way to P of them. We would have these indexes. And as we saw in the hospital example, if we sum over them, we should get P. So in our example where we had repeating every year, so 12 months, if I sum them up, you should get 12, okay? And so you could think about what is this doing if all of your seasonal indexes were 1, you're basically equally weighting what you expect will happen. But if one of them should be higher or lower, it's representing kind of the average amount. It would be above or below our kind of deseasonalized idea. And so it's really a normalization method relative to the average. So that is what's going on is if January is a low month, we will have a seasonal value that's smaller, less than 1. If June is a big month, you'll amplify that. Okay. So hopefully that makes sense. And to test your knowledge on that, here is my thought question for you. So which of the following could be seasonal factors used in Winters method with a season consisting of 3 periods? So the frequency is 3. Which one of these is valid seasonal factors given we're using a multiplicative method? So please pause the video, think about this, maybe do some calculations in your head. Hopefully you got the answer B. B is the correct answer. And why? So first of all, if you have a frequency of 3, we need a seasonal index S1, S2, S3. So, C is kind of an oddball. We need a factor, a seasonal index for each of the periods in your frequency. So, C is wrong for that reason. But then you have A, B, and D left. And the other key piece of information we need to determine which one is correct is over this, we should sum it up to our frequency. So our frequency here is 3. So if I sum up A, this does not equal 3. If I sum up B, this equals 3. That's why the correct answer is B. If I sum up D, this does not equal 3. So what is going on here? B is the correct answer. What you can also see is that the first period is lower than average. The second is average, and the third is much bigger than average, okay? And then this repeats over time. And so you could see if we started to the next one, we would expect it not to keep going up. Instead, you know, in the next period, it would be lower than what we had before, right? Because this keeps repeating. So B is the correct answer. All right, so now we have all the pieces to actually do Winter's method. This is an application directly of, at the beginning of, you know, slides B2, I talked about, there are these steps in implementing a time series forecast. Winter's is a time series forecast method. So we're going to follow the exact same steps. They're just a little bit more nuanced because we have a few more things to do. So the first step, as a reminder, was to plot the data and identify the systematic components in the data. And so if we identify there's a seasonal variation in the data, we also need to identify how long that happens, the frequency. So again, if you have every month, we have a different one. So you could think about P of 12. You might have a weekly one, so P of 52. You could also just say something that doesn't have to do with the calendar. For example, maybe you supply training materials. And if your training session is 6 weeks long, maybe P is 6, right? And so it is whenever these things repeat, that is your frequency. So there is an extra step. You have to identify the systematic components, that it would have a level, trend, and seasonality. But if it has seasonality, what's the frequency of that? And then select an appropriate model of demand versus time. And so again, if they have those 3 components, Winters is a appropriate model for those systematic components. And then we need to create the forecasting model. Just like we've seen in the other time series methods, we have to initialize. One thing to note here is we actually need a full season of seasonality factors. And so if you have, let's say, 12 or 52, I need 52 pieces of data as initialization. So it's a little bit more data heavy. Again, the beauty of R is we won't have to worry about this, but if you did this by hand, it gets a little messy. And then we would actually calculate these different components. And then we need to set the smoothing constant, set the parameters. We'll talk about that in some previous slides. Then we'll use the model to predict it and potentially update it as needed. Okay, so let's walk through that. So if we plot this data, and this one's not quite as obvious as the retail one, but you can see it does seem to have something that keeps repeating. Like here's a point, here's a point, maybe here's a point, you know, right? There's like something going on, right? And so if you want to identify the interval or the frequency, the trick is to take a peak to peak, valley to valley, and count how many pieces there are. So if I take this one, but one thing to note is it's like putting together wallpaper or something. You want to get so that I start here. So I want to end at this point here. So I want to count how many of them are there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Okay, so then that would mean that P would be 12, but that's usually not enough. You shouldn't just do it on 1. You should make sure, okay, if I count from 12, if I start here at 1, do I get, you know, somewhere over here at 12, right? So we should confirm that it repeats. And so for this example, you know, the peak here is a little less than, you know, you wouldn't necessarily see. There's some error rates, but it seems okay, and you could keep doing this. Okay, so you should confirm that over time you get the same kind of repeating pattern. So there we would have the frequency of 12. The next step is to then create the forecasting model, which again, for these time series models, it's basically setting alpha, beta, gamma now and getting a forecast. And so mathematically, these are the equations. We have an equation for level. One of the things to note is this looks similar to what we've seen before. We have an alpha, 1 minus alpha, but what do we have going on here is we have deity. Remember, deity is our observed data, but we're dividing it by the seasonal thing. So this is sometimes what's called deseasonalized data. So I want to know the demand, but maybe it's just higher because it's in November and that's a high period for us. So you can think about, we are using deseasonalized values here. Then the trend, again, the trend has to do with, am I going up or down? And so one way to measure that is kind of using this deseasonalized aspect. Do I go up or down one period to the next? And then the seasonality, here you can see we are using the demand divided by the level, and we're trying to figure out, on average, I have this level value. You can think about the level as kind of my average, right? So if I'm in this period above that, that would give me a seasonal factor that's above 1. If my demand this period is less than my deseasonalized kind of measure, that would give me a value that's less than 1, right? And so you could think about that seasonal index. If it's greater than 1, I'm amplifying what I would expect if I didn't have any of the seasonality. Versus if it's less than 1, I'm saying, oh, that's a low period. So it should be less than I would expect if it didn't have the seasonality. And then, so you see now I have an alpha, a beta, and now a gamma. We'll talk about how to set them in a previous next slide. And then we have a forecast. So this forecast is a little bit uglier. One thing to note is you can see, if we look at this equation without the seasonality, that looks very similar to our exponential smoothing with a trend. So we have the level plus m periods out times the trend. So you could think about that as exponential smoothing of the trend, but now I want to say, yeah, but in this season, so let's just say we're in January. Why is it plus m and t? It gets a little bit ugly, is that we need to make sure we're capturing the right January and January. So this is like a record thing, if February and February kind of thing. And so what we're doing is then saying, should it be a higher or lower amplification or de-amplification based on our seasonality? Just like we've seen before, we need to initialize. So for example, to get L of t, we need L of 0, or L of 1, we need L of 0. T of 1, we need T of 0, but then we need a full set of seasonality for that. And then we also need to set these 3 smoothing constants. Okay, so to set these 3 smoothing constants, how do we do that? Again, just like we did for the other ones, we would want to set them in a way that minimizes mean squared error. But just to kind of emphasize, what do these do? Alpha determines how much weight is given to closer versus further observations. Beta in terms of trends, and then gamma in terms of seasonal factors. And so just as an emphasis, these are all exponential smoothing. So they're all, Winter's method gives more weight to closer pieces of data. However, if I change alpha, beta, and gamma, it's how much, like how extreme is this weight? Is it really extreme and then falls really flat? Or is it more of a gradual exponential curve? And so that's what alpha, beta, and gamma are doing, but it's doing for all these separate components. And so how would you set them? You would set them simultaneously by minimizing some error measure. The beauty of R, in one line of code, it does this. It solves this nonlinear optimization model and does that behind the scenes. And so, then once you have that, so once you know what alpha, beta, and gamma are, you can actually use it to forecast. So I want to emphasize, when we go over this in R, we do 2 aspects of R. We do all the stuff with this Holtz-Winters function. That's to get the alpha, beta, and gamma. Then we write another line of code that uses this forecast function, and that's when you're actually taking in these alpha, beta, and gammas and forecasting into the future. So that's then using this equation. And then we would observe, so demand would actually happen in period t plus 1, and so we would observe it and maybe update and adjust. Okay? And we will implement that in R, and R is awesome and really helps us do that. All right, so my next kind of thought question is to make sure you're kind of following along, understanding what's going on. So if the historical demand indicates there's a systematic components of level, trend, and seasonality, and the seasonal factor for period 101 is 0.85. If nothing else changes, the forecast for T equals 101, considering seasonality, will be blank, the forecast just considering level and trend systematic components. So this question basically asks if I consider the seasonal aspect, and for this one, the seasonal aspect is 0.85 as our seasonal index. Will you get a value for your forecast that's bigger, smaller, or the same if I didn't have that seasonal component? So hopefully you answered A. So by having the seasonal component, what I'm going to do is I'm going to basically estimate what I would have without it and then multiply it by 0.85. And because that value is less than 1, it will make my estimate lower than if I ignored seasonality. So A is the correct answer. So my last kind of slide I'm going to stop with is to realize that we assume on the x-axis that these things repeat in kind of a continuous way. That doesn't always happen. So there are seasonal things that don't repeat every, let's say, 12 periods, 15 periods. Specifically things that deal with the lunar calendar, so Ramadan or Easter, they can occur, like if you sell things that are associated with these holidays, you should expect a seasonal effect. However, it might not be perfectly repeating. And so we in this class are not going to deal with that. We're going to assume that these are repeating. There are methods that can capture these things, but just be aware of them. I think it's important to realize. The other thing to realize is if you start out and you basically have these seasonal factors that are all really close to 1, or they really widely vary from season to season, then this might not be appropriate. So if they're really close to 1, you're basically not really amplifying, de-amplifying using seasonality. So maybe a different model that captures different things could be useful. And if they're really going kind of crazy, again, we might not have the best model. And so in the next video, we'll implement this in R, which is awesome compared to doing this by hand because you have to keep track of all these things.